limit, which is SC, modifying factors. Okay, so we have used the notation SE to denote endurance of the material in machines. That's the specimen which is actually being used in an element, a machine element. So it's manufactured with that element. So that's the SE when that material is tested in the machine. But when we talk about test specimens, we use SE prime, and this is a lab tested endurance. So it turns out that SE, which is the one you get in the machine element or in practice, is always less than SE prime or less than or equal to. And that's because when we take an element in the lab, we take special care to see it's uniform, there are no impurities, it's machined properly, it's polished, and so on. And those kinds of perfections are not there when the part is in a machine. And so there are factors which modify SE, right? And so there is a relation between SE, which is the endurance of the material in the machine, to SE prime through these modifying factors. There's one more KF, okay. Okay, all these Ks are either 1 or less than 1. They're not negatives there. So clearly, if you multiply SC prime with a host of factors which are less than 1, you will get something which is less than SC prime. So what are these factors? We talk about them in one at a time. Ka is a surface factor. Kb is the size factor. Kc is the load factor. Kd is the temperature factor. Ke is the reliability factor, and Kf miscellaneous Okay, so one way of figuring out what SE is you can do some essentially it boils down to a bit of physics and figuring out making up theories why each of these factors would affect the stress and the endurance, and then having a model based just on the material properties, right? But the other way to do it, and which is the practice followed in machine elements, is we don't really do too much build a theory behind why the endurance is low based on the microstructure. We just do tests, and once the test results come out, we make up a factor by sort of fitting data. And that's the approach which is taken here. These factors come from empirical tests done on specimens which would have, which the surface would, for example, if the actual surface is polished, will then not polish it so much, do tests till failure, find how that endurance is changing, and come up with a factor for the surface. Same for the size and so on. So what is going to follow is a bunch of numbers, okay? And the goal here is to learn how to use those numbers rather than understanding why those numbers are, what those factors really do. So that's the approach here, not really understanding much about the theory behind it, which is again something which you can learn in a higher class. So let's start with the surface factor. sorry, surface. Again, this is because specimen is polished, but machine, but the one used in the machine is not. So clearly what you need to do is you need to take the test specimen and now have various amounts of polishes given to it, and then do the same test, figure out how the material fails, and then have some kind of empirical fit. So what they found was that this factor only depends on the tensile strength. Okay, these B's and A's are different from the A's and B's, which we use for the ideal SN diagram. So SUT, yeah, yeah, and I'll give you a table. SUT is tensile, AB are constants, not the same. I wish they'd use a different symbol for this. Yeah, and this is really dependent on the material. So okay, so here are the constants. So for ground, when it is, so this is when you take, I think this is for steel. If you ground it, that's the A, that's the B. This is the A, this is the B. This is in kpsi, this is in MPa, the B doesn't change. So then if this is the machining process, machined or cold drawn, then you use the other one and so on. So you need to know the manufacturing process in order to find the right A and B. Okay. And this is again from the book, and it'll be in the notes. Okay, so let's move on. Surface factor. Next is size factor. That's KB. Okay, now this is a little bit more complicated. So when we did this test, and this was some time back when I showed you the test specimen, when you load that test specimen, you actually rotate the specimen. And so, and the specimen is round. So what I'm going to first present is the value for KB for rotating round specimen, like the one I showed you previously. And the two ways you can have this. One, you can have bending and torsion, and they would have the same KBs. So here is the KB. It's 879 d raised to So when do you use them? Well, if the diameter is between 0.11 and 2 inch, then you use the first one, or if it is between 2 inch and 10 inch, you use the other one. I believe that beyond that range, you just ignore the value of KB. You'll just use a value of 1.
Wait, so what happens if like you get like a D of 2.
Yeah, you'll use this one.
Top one.
Yeah.
So then the bottom one would not have the equal.
Oh, I didn't. Oh, sorry. Yeah, it should be less than 1.24 d raised to then 1.51 d raised to 157, and the top one is for 2.7951 millimeters. The bottom one is that is less than nicely. Okay, so clearly the top ones are in IPS, the bottom ones are in SI. If you have an axial specimen, that is, it's loaded in a uniaxial tension or compression, then you would have a KB of 1. Okay, so remember this is for rotating round specimen. Okay, but then your actual element can be non-round, it could be non-rotating. So in this case, you have to use the following formulas. Let's call this 1, let's call this 2. Second one is non-rotating round specimen, or if it's a non-rotating specimen, sorry, non-round specimen, rotating or not, you should use these formulas. The issue now is that for non-round specimens, like let's say square specimens or rectangle specimen, there's a breadth and height, and how do you relate it with D? So what they do is there's a theory called critical volume theory, and without going too much into detail, I'll just state what the theory says and then show you how to use that theory to find, based on the cross section, find an equivalent diameter, and that equivalent diameter will then be used to find KB from these formulas. Okay, so this is how it goes. So there's a critical volume theory which says that volume of material experiencing (95% of maximum stress is critical. Okay, so what we do is we equate. So it says that basically anything above, which is the part of the material which is experiencing 95 and above % of stress, is the part which is critical and should be used for fatigue testing, developing fatigue test equations. And so what they do is they equate the volume of 95% stress of non-rotating specimen equals volume of 95% stress of rotating ground specimen. Okay, so when you equate the volumes, the lengths are the same, so lengths drop out, and so you're only left with equating the areas. You need to equate the areas. Okay, so Okay, so here is what I mean by this. So let's see, rotating round specimen. So the round specimen, okay, so this is a perfectly solid specimen, just that I'm drawing two diameters. One is the outer diameter, which is DE, and then the inner diameter, which is 0.95D, 0.95 DE. What we're trying to do here is equate this, find this area. So that area is, what is the 95 sigma, or the 95% of the area which is important for fatigue failure. So DE square minus 0.95 DE square. So when you simplify that, you get A 0.95 sigma equals 0.766 DE square. So let's call that 1. Okay, so let's call this 1, 2, non-rotating round specimen. So here, what they do is they take 0.95D, okay, and the area outside this, so this area in yellow is the one which they use to find the 0.95 sigma. So that is, so you can actually compute that by doing a little bit of math, right? It's, you know, the distance between those two parallel chords, and given that, you can find that area. Okay, so let's call this 2. So now to find the equivalent diameter, you just equate 1 and 2. So if you equate that, you can find DE 0.37D. So that's only for a non-rotating round specimen. We can do this for a rectangular section. Okay, so again, for rectangle, find the 95% area. So A 0.95 sigma is it's going to be 0.05 BH. Let's call this 3. Again, what you do is equate 1, the round one, to 3, and then solve for DE. Okay, and so as I said, what you need to do is, I should have put this here. If you go back to the equations, so if these equations, let me put a star to them, then what you'll do is, once you find DE, use DE in the equations which are written by star. Okay, so since there is no equivalent diameter for, say, for example, a rectangular section, you do this equation, you do this thing which I showed you, and then use this particular effective diameter in order to substitute for D, and then get the size factor KB. And then I have a table of other size factors for some other geometries, which I'll just put here. This is a table from the book. Insert. Okay. And I think the first two ones I showed, I talked about are right in the first two ones there. So this one and this one was discussed, but if you want to find for other sections like the I section, it would be here. Okay, let's go to load factors KC. It's called a loading factor. And this is fairly straightforward. KC will have one of the three values, depending on the type of way in which you load it. One for bending, 0.85 for axial loads, and then 0.59 for tension. So just find the way in which you load the specimen and then use one of those factors. Okay, we are almost there. So next one is the temperature factor. That's kind of a very important one. Right? Materials are subjected to temperatures which are different from the temperatures they experience when they are tested. So this factor counts for that. So this is D. Okay, so first of all, what you need to know is you need to compute this ratio. And I'm going to define what ST and SRT is in a bit. So ST divided by SRT is 0.98 plus 3.5 10 raised to negative 4 TF minus 6.3 10 raised to negative 4 TF, sorry, negative 7 TF square. So this is clearly TF is temperature in Fahrenheit, and I'll put it down in a bit. ST divided by SRT is 0.98 plus 5.9 10 raised to negative 4 TC. That's temperature in Celsius. So let me write down what these numbers are. So ST is ultimate strength at the operating temperature. And SRT is the ultimate strength at room temperature. So this ratio is clearly telling you how the ultimate strength will change as the temperature of the environment will change. So TF is in Fahrenheit, TC is in Celsius. Okay, so that's just we're just getting started. So once we found this variation in strength, we are now in a position to find the factor KD. And there are two cases. One is that SC is known. Sorry, SC is unknown, my bad. Okay, so here's what we'll do. First, let me call this equations with a similar sign, and so I'll refer them. So first, what we do is estimate ST divided by SRT using tilde. Then estimate SUT. Okay, SUT is the ultimate strength at the elevated temperature using this equation. SUT at elevated temperature is this ratio ST divided by SRT, which we found in this step, times SUT at room temperature. So typically, you know the tensile strength at room temperature, and you're trying to estimate the strength at the elevated temperature T. Finally, we can estimate SE, which is the actual endurance strength, by this formulas. .5 SUT for 100 kpsi. We've seen these equations before. They were used in the idealized SN curve. So this is for SUT less than 200 kpsi. SUT is greater than 200 kpsi. If you want to use in SI, then we have 0.5 SUT and 700 MPa, and this is for SUT is less than 1400 MPa, and here this is if SUT is greater than MPa. Okay, and then clearly KD equals 1, SC equals SC prime, and you're all done. Okay, there's a case when SC is known. So SC prime is known. That's the next one. Second, SC prime is known. In this case, the steps are estimate ST divided by SRT from the formula I wrote down earlier, the one with tilde. Then estimate KD as ST divided by SRT, which is clearly comes from the first step. And then finally, estimate SE as KD SE prime. Okay, and so a lot of things here are going on, but hopefully I'll put everything together in a few problems. So after we finish this, we're not too far. There's two more left. We'll do problems probably in the next class. So then is the reliability factor. This basically talks about how reliable is the machine element compared to the test specimen. Now, reliability is something which you know in advance, right? When you machine a part, it's produced in such a way that it is reliable to 99% or 99.99%. So given that information, you can predict the KE. It's 1 minus 0.08 ZA. And what is ZA? It comes from this table. So it actually does go a step further. The table gives you directly, it gives you the factor ke. K is right here. So you don't have to even use the formula. You can just, given the reliability, you can directly find ke. Okay, so last one, kf. And kf, they've not really given a factor. They've not given a value, but you've told different effects which could change modify the endurance strength. So miscellaneous factors. They are, well, corrosion. So this one you will be explicitly given what's the factor for, say, corrosion. Electrolytic cyclating, metal spraying, cyclic frequency. So if you cycle it around, endurance changes, fretting, corrosion, and there are more in the book, but I just picked a few. So that factor, fretting, Fretting.
Cyclic frequency.
Yeah, cyclic frequency. Okay, so that factor will be given to you. So what we'll do next time is, we will solve about 4 problems, and I can post these problems beforehand. A couple of problems. So I'll post them, and so you'll have them, and so we can just proceed with solving the problems. Let's go. Interesting. Okay, so I'll see you on Wednesday. Your 50% of exam is graded. Waiting for the TA to finish grading, and then we should hopefully have it out by Wednesday.
Better on this.
Let's do them a few problems and just do them. Hopefully that will give you a good idea on how to use these factors. Okay, steel has a minimum ultimate strength of 520 MPa. So that is SUT is 520 MPa. Estimate K. So what we need to do is go back and see how we find Ka and then use that. So let's go back to the part where I talked about Ka. So the surface factor K is A times SUT raised to B. And in order to find A and B, we need to know what is the surface finish. So what is the surface finish? Well, it is the machine surface. So let's see if there's a table for machine surface. Yeah, there it is, machined or cold drawn. So A is 2. And well, sorry, my bad. You only need this if you're using in KPSI IPS unit. This is for MPa. So we need 3.04 and B is minus 0.217. So let's just use that. Back, write the formula for Ka. A times SUT raised to B. A from the table is 3.04. SUT is 520, and that should be an MPa. And B is minus 0.217. So when you do the calculation, it comes out to be 0.78, and that's your answer. Yeah, it's very straightforward. Okay, next question. A steel shaft loaded in bending is 32 mm in diameter, buting a filleted shoulder 38 mm in diameter. Estimate the factor Kb if the shaft is used in rotating mode and non-rotating mode. So we need Kb. Again, there are 2 modes, and let's just go to the notes and see what we need to do about finding KB. Okay, and then we can refer back to this numbers here. So going back. Okay, so if you see this, there's one set which is for rotating round specimen, and there's another set for non-rotating round or a non-round specimen. So here we're interested in rotating round specimen because we are given a diameter. So we need to use either this or this. It really depends on the choice of units, right? So if you have IPS, then use the top one. If you want SI, use the bottom one. So in this case, let's go back and see what, okay, so I forgot to say this, but we need to identify which mode it is, bending, torsion, or axial. I think it is bending. Let's go back. So bending, and we have 32 mm diameter. So what this means really is that it's something like this. This is 32. This is 38. And the reason why we'll use 32 is because there's the smaller diameter, which is usually the problem. That's where the stress is higher. So 32 mm is what we'll use. We'll go back to the table. So bending, that's what we stick to. Since this is 32 mm, which is between here, right? So we need to use 1.24 times d raised to minus 0.107. Let's just use that. So from strict, okay. We just, you know what, let me just copy paste that. It's much easier when you refer back to the notes. So I'll put everything in the blue box, which is something which is copy pasted from somewhere else. Okay, so let's use KB, the top one, 1.24. D in this case has to be in mm. So 32 minus 0.107. Okay, so that comes out to be one, it'll always be less than one, my bad, 0.86. And this is the solution to part A, rotating mode. Now let's see what we have to do for non-rotating mode. Let's go back. Yes, that's for the rotating mode. For non-rotating mode, we need to use this concept of equivalent diameter, right? And so for non-rotating round specimen, what we need to do is we need to equate this area to this area. And if you do that, you get D equals 0.370D. So if you copy that, and by the way, it's for non-rotating round specimen. Okay, so we find the equivalent diameter. It is 0.37 times 32. Okay, that comes out to be 11.84. Okay, and then once we have the equivalent diameter, we sub in the right value for the equivalent diameter in the formula shown above. So from asterisk, we have KB equals, so use the top one, 1.24 7.84. Okay, so that comes out to be 0.95. So KB 0.95. So which means that if you see here and here, you'll see that the KB has increased, which means the endurance wouldn't be lowered that much, right? The lower the KB, the lower would be the endurance, because KB times the endurance in test specimen. And we can understand that because when a specimen is not rotating, it will probably take in more stress than it would if it was rotating. So it's no wonder that this factor is greater than part A. Okay, so this is the flavor of the fatigue calculations. It's basically, there's a table you need to refer, you need to know what you're doing and go with the computations based on the empirical evidence. Okay, Q3. So 1035 steel has a tensile strength of 80 kpsi, and it needs to be used for a part that operates in a steady temperature of 750 Fahrenheit. Estimate the endurance limit at operating temperature. If, oh, I forgot to put part of the question. Okay, I should finish this. A, the tensile strength room temperature is known. Okay, that is, we don't know the endurance limit. And then B, the room temperature endurance limit is, now it's SE prime at, so the room temperature here is taken to be 70 degrees Fahrenheit, is 39 kpsi. Okay, so how do you deal with the fact that you need to account for the temperature, right, in this case, because you're given the endurance at a certain temperature, which is at room temperature, and you need to find its endurance at a different temperature, the operating temperature, which is 750 Fahrenheit. So let's just go to the effect, which talks about temperature effects. Okay, this should be next one. Here it is. Okay, so what we need to do is, there is this factor which basically gives us the ultimate strength at operating temperature T divided by the ultimate strength at room temperature. RT is room temperature. Okay, and the top formula is for Fahrenheit scale, and the bottom one is Celsius. Clearly, we want the top one. So that's the first part. How do you find the ultimate strength as a function of room temperature and the temperature TS? Now, there are two cases here. One is SE prime is unknown, which is the first case in our problem. And then the other case, which I think is the next page, is SE prime is known. Okay, so let's just focus on doing the first part where SE prime is unknown. Now, the algorithm is here, right? So let's just use it. So I'm just copy paste that. Okay, so we're solving for part A. So this is the algorithm. Okay, paste. Okay, so let's just proceed with this. Just estimate the first thing, second thing, and so on. So let's estimate ST divided by STRT. For that, I need the other formula, which I should copy. So let's just take the other formula, which is right here in Fahrenheit. So that's the formula I'm going to use. And maybe I should box this so that way you know it's copied, pasted from somewhere else. Just box this also. Okay, let's just do this calculation now. ST divided by SRT is 0.98 plus 3. Times now temperature is 750 minus 6.3. So this is our, let's create a different symbol for this, say 1. Okay, SRT is 0.89. Okay, and then I should probably, I should have probably done this. This is 1. This is the number 2, which I'm trying to do. And this is the number 3. Okay, so I'm just going to follow this. So if I found this factor, then I want to find SUT at the elevated temperature, operating temperature T. So I'll use the second formula now, part 2. SUT at the elevated temperature equals this ratio times SUT at room temperature. So SUT at elevated temperature is unknown. This ratio is 0.89, and we do know the temperature, the tensile strength at room temperature. It is given as, I think, 80 kPa. It's right here. Okay, so that is actually at a room temperature, which I think is not explicitly stated here, but it is at room temperature. So let's put that in. And so we get SUT at 750 equals, but it should be 750. 71.2 kPa. Okay, step 2. So we're done finding the ultimate strength. The third step is, if you go back, it is estimate SC using these formulas. The top one is for kPSI, the bottom one is for SI units. So let's take this one, right? Because we want in kPSI. Copy, paste. Okay. So which one do we take? Well, we take the one which depends on the tensile strength. Here we have 71.2, and note that this is at 750. Okay, so SE is 0.5 times 71.2, the top one. And so SE, by the way, this is now SE at 750, right? Because we're using SUT is at 750. Just to make that clear. 750. So SE That's 750 is 0.5 times 71.2. And so SE at 750 is half of that, so 35.6 kpsi. Okay, so let's, yeah, question.
So SUT is the ultimate strength, right?
Yeah.
So then why do we use the tensile strength for the ultimate strength?
Why do we use ultimate strength?
Or no, why do we plug in the tensile strength into the ultimate strength? Is SUT ultimate strength?
Yeah, it's ultimate strength.
Yeah, so if we use SUT at room temperature, why do we use the tensile strength for that variable?
I didn't quite follow. Maybe it's,
Okay,
it's
so
the,
SUT at 750
uh-huh.
equals ST over SRT times SUT at room temperature.
Right.
So then we plug in tensile strength into SUT.
Yes. You mean this one? Let's just go slowly. So
Number two.
you mean this one?
Yeah.
Okay.
So we plug in tensile strength into SUT to the ultimate strength.
Yes.
Yeah. So are they the same?
Yeah. So in this case, let's see the problem. I think the this is, when they say tensile strength, it just means that, so tensile strength for what? So tensile strength to failure. So it's the ultimate tensile strength. So in the absence of the word ultimate, we assume that that's the ultimate strength. So that's where that stress strain curve takes that inflection. It's just it reaches the maximum. Okay, good question. Okay, so let's go to the next part, which asks us to do the same calculation, but when we know the endurance limit at room temperature. So, okay, 70 degrees. We know the endurance limit at room temperature, which is 39 kpsi, which is different from the fact that we did not know in the first case. So let's take that information and proceed. But before we do that, let's see what we know about the empirical tests on this. So if you go and check the test, so here is, this is unknown. This is the part where it's known. So what if you know SE prime? If SE prime is known, then follow this procedure. And so let me just copy this. Okay, so this is part B. So what is SE prime? It's known, it's 39. So SE prime is at, by the way, 70 degrees, right? Because it's at room temperature. So it's 39 kpsi. Okay, so let's just use this. Let's call this 1, this 2, this 3, and let's go 1. So estimate ST divided by SRT. Now that's going to be the same, right? Because it's basically the ratio, and we already computed that. So if you go back and see the formula, here it is. Right, we already did this calculation. It's 0.89. So let's call this 1. Let's see. Okay, done. Next part. Estimate KD. KD is ST divided by SRT, and that's easy, it's 0.89. And the third step is estimate SE, which is KD times SE prime. Now we are assuming that the other factors, KA, KB, KC, KE, KF are equal to 1. We are only studying the effect of operating temperature. So we assume them to be 1. And that's why this formula reduces to the following, as I showed it here. So this is 750, provided we have 70. So SC at 750 is 35 kpsi. Okay. Okay, here is this is the last question now, question 4. This is probably the most elaborate question you can get for in something like this, where you're, you're trying to find all those factors. One thing which is missing in this problem as it stands is the ultimate strength. So SUT at 70 degrees is given, and it is 112 kpsi given. Okay, so let's read the question. So a rolled steel bar has been machined to a diameter of 1 inch. It is to be placed in a reversed axial loading for 70,000 cycles to failure in an operating environment of 650 using ASTM minimum properties and reliability for the endurance limit of 99%. Estimate the endurance limit and fatigue strength at 70,000 cycles. Okay, so we need, let's see, we need the endurance limit and the fatigue strength. Okay, and the fatigue strength, by the way, is given by this formula, right? And we need to essentially put to find SF. Okay, so that's I'm sort of trying to work my way backwards. And the question is, what are the things missing? A and B is missing, right? We need, if you know A and B, then we can use that formula. But what is A and B dependent on? It turns out that A is dependent on this factor F, SUT square divided by SC, and B is 1/3 log to the base 10 SC divided by FSCT. Okay, so we have SUT, which is unknown. Well, SUT is known, it's at 70. But we need to find SUT at the operating temperature, which is 650. So here temperature is 650. And then the F, there's a formula for F. It is 1.06 minus 6.9 P square. And this should be at 650. So there's a lot of things going on here, right? It's like a lot of things we need to find. We can just list them here. So we need, so I'm going to make a list of things we need. So we need to find, of course, A and B, but A and B depend on F, SUT, and SE. So we clearly need SE, right? Then we need SUT at 650. And I think that's about it. If you can find these two things, we can get the rest of the things. Okay, and what will help us to find SE? Well, SE is KA, KB, KC, KD, KE, KF, SE prime. So we need to know SE prime now. And then if you want to find SUT at an elevated temperature, let's say 650, then we need to use this formula, ST divided by SRT, S times SUT at room temperature 70. And I think SUT is given to us. So this is given, this is unknown, and we can be able to find, okay, so that means we need to find ST divided by SRT. Turns out that ST divided by SRT is only temperature dependent. It is 0.98 plus 3.5 TF. Okay, so what I've put here is like all over the place. It's just me thinking about what are the different things we need. So now when I'm going to solve it, I'll solve it in linear fashion, okay? But first, I think you always want to think of what do you want by going backwards a little bit. Okay, so we need to find, it looks like this is super easy because this is 650. SU at 70 is given. This is easily found. SU at 650 is pretty straightforward now, given all that. SC needs to be known, but SC depends on SC prime. And SC prime, there is actually, okay, I forgot one more thing, last thing, and then we'll start solving it. So there's a formula for SC prime. It is, and I wrote it down multiple times. So depending on the range, you can either have F.5 SUT or 100 kpsi. Okay, so that would be the last one. So assuming that we found that, which is pretty easy now because you know SUT, we need to find all these factors. And that's where we have to go and look at the tables. So what I'll do is, the way I'll approach this is, I'll try to find the basic quantities, right? So I'll make a list of things I need to find. I need to find SC prime, I need to find KA, KB, KC, KD, KE, KF, and then I also need to find ST divided by SRT. So these are the fundamental quantities, which once found, it's super easy to get what we need. So compute these first. Okay, so let's just do that. Let's find these first. this is the actual solution. Okay, that was just me thinking about what sort of things I need. Okay, so let's proceed to find SE prime first. So SE prime is, as I said, 0.5 SUT, because the stress is less than 200 kpsi. So 0.5 times SUT is okay. Hold on, there's a problem here. Okay, so I know the temperature, I know SUT at 70 degrees, but the issue is I'm really trying to find SE prime at 650, which means that I can't solve for SE prime unless I have the strength at 750. So it means that I first need to get this thing, and then I can find SE prime. So let's change our plan and then start solving for S. I'm going to solve for ST SRT first. My bad. ST divided by SRT should be the first thing. So that formula is 0.98 plus 3.5 10 raised to negative 4 TF, which is 650, minus 6.3 10 raised to negative 7 650 squared. So this comes out to be 0.94. Okay, and this is all I need to find the ultimate strength at a different temperature. So the formula is SUT at 650 is ST divided by SRT, which we found, SUT at 70 degrees. So SUT at 650 is 0.94. SUT at 70 degrees is, when that was on the question, it's 112. And so this comes out to be 105. Okay, so with that, let's now proceed to find SE prime. It's 0.5 SUT at 650. So it's 0.5 times 105, which is 52.5 kpsi. So that's done. Let's move on to C. Let's get the factors. K, A, KB, KC, KD, KE, KF. Okay, so for KA, all I need to know is the surface finish, and the surface finish is given in the problem. Let's see, it is so hot rolled steel bar. Something about hot rolled steel bar, maybe, perhaps. Let's see. Okay, I need to find this in my notes now. Oh, there it is. So hot rolled, there it is. So for hot rolled steel bar, we need to use, and this is kpsi. So I need to use seems like I used machined or cold drawn. Why did I use that? Machine to, okay. Okay, so it's hot rolled steel bars in machined. Okay, so this is the keyword I need to look for. K. Good catch. Yeah. So I need to go and look at. My God. Oh, something moved. Thought I had it in the first page. Oh, there it is. Okay, here. Okay, so I need to use machined. So it's A is 2 B is minus 0.217. And remember, I have the ultimate strength in kPSI, so using that. So let's go there and then write K, which is A times SUT raised to B. A is 2. The strength is 105. And B is minus 0.217 equals 0.73. Okay, KB. Now, this is under axial load, I believe. Axial loading. For axial loading, KB is 1. So it's super easy. So KC. So if you look at the table for KC, it's basically lists loads. There is a one for axial loading, one for bending, and one for torsion. And so in this case, axial loading, the factor is actually 0.8. Okay, and that's something I've given there. Let me not go back to it, but it's very simple. Okay, KD. Now, for KD, remember there was a way to compute it, but it depends on whether you know SC prime or you don't know SC prime. So if you go back and see KD, okay, so in this case, the endurance limit was not given. And we estimated the endurance limit using this algorithm. We actually found it as 0.5 SUT, and SUT was at the elevated temperature. In that case, we need to assume KD equals to 1. And so that's what I'm going to use here. It is 1, since SE prime at 650 was not known. Okay, KE. We've never done any problem with KE. Let's look at the formulas for KE. KD. Yeah, so KE is this formula. However, depending on the reliability, and I think it is 99% reliability. So that's the reliability which is given for the specimen, and it's in the table. Actually, I should have mentioned it in the problem. So in this case, the reliability factor is 0.814. Yeah, it's given here, 99%. So 0.814 is what I need to use for KE. That's for 99% reliability. Okay, so we've done with all the fundamental things we need to compute as per that. Now, let's go back to our list of things we needed to compute. And just check mark all things we've done so far. So we completed this entire list. I think we've got everything there. Now, we were trying to do all that because we wanted to find SE. Yeah, SC, which is now very easy because we have all these factors. And of course, KF is 1, which I did not mention. If you're given KF, you'll be explicitly told what KF is. KF is a miscellaneous factor. SC prime has been computed, so SC is very easy. Once we get SC, we need to find F. And then we need to find, what else? I think that's it. Once you find F and SE, we can find A and B. So the next list of things would be F and SE. Second set. And then the final set. Yeah. KF is not given. Oh yeah, it's a miscellaneous factor. If you have some corrosion or some other effects, then you'll be told of what factor. Just put 1, which means it has no effect. So once we find FSC, we'll find A and B, and then we are pretty much done. So let's go on to find the second set. F is 1.06 minus 2.8 to -3. It's the strength at 650, so it's 105 plus 6.9, 10 raised to negative 6. And I believe I wrote the formula in the previous page, 105 square, and that comes out to be 0.84. And SC is Ka, Kb, and so on. So it's going to be, I'm just going to put all the factors now. 0.73, Kb is 1, Kc is 0.85, Kd is 1, Ke is 0.814, Kf is 1, and then the endurance limit is 52.5. So this comes out to be 26.5 kpsi. Okay, so that's the second set. And finally, we need to find A and B, the third set. So A is FSUT squared divided by SC. So that's 0.84 times 105. This is the strength at 650 Celsius. So 650 Fahrenheit, 26.5. A is 293.6 kpsi. B is 1/3 log base 10 SC divided by FSUT. That is 26.5 divided by 0.84 times 105. So that comes out to be minus 0.1741. Okay, so now SF, which is one of the things we asked, is AN raised to B. A is 293.6. N is 70,000. B is minus 0.1741. So SF is 42.1 kpsi. That's answer to one part. Then the other thing which was asked was, what's the strength at, I think strength at 650. So the strength at 650 is a part we computed. It should be here somewhere. Yeah, SC. So this SC prime is actually the strength at 650 because it's using 0.5, well, it's using this ultimate strength at 650. So SC, wait, is that the one? Okay, my bad. This is the SC we want. So this is SC. Okay, this was SC prime at 650, and this is SC at 650. Right? This is the endurance limit after accounting for the factor. So the answer is 26.5. So that's a fairly elaborate question, which sort of takes in all the different things we learned in this fatigue chapter so far and puts it all together.